This is a short lesson about sine, cosine, and tangent. So here we are looking at a triangle. It's a right triangle, and what that means is it has a side which is 90 degrees, and we can designate that with this little squared off symbol. Now, to introduce what sine, cosine, and tangent are, I'd like to define them using the properties that are particular to a right triangle. You may have taken a geometry class or a trigonometry class where you applied sines, cosines, and tangents to triangles that were not right triangles. And that's the more advanced use of sine, cosine, and tangent. So we're going to begin just by focusing on right triangles that have a 90-degree angle. Now, just another refresher about triangles is there's a rule. All the angles inside the triangle have to add up to 180 degrees. And so we've already got a side that's 90 degrees, and so when we add up the angle over here at the right and the angle up here at the top, together those must equal 90 degrees because all three of them put together always, always, always have to be 180 degrees. Now I've added a couple of triangles. I've drawn a green triangle, which is smaller than the original black triangle, and I've drawn a blue triangle, which is larger than the original black triangle. By smaller and larger, I mean that the sides have different lengths. The lengths of the green triangle sides are smaller than the lengths of the black triangle sides, and the lengths of the sides on the blue triangle are longer than the sides on the black triangle. But all these triangles have something in common. They all have a 90-degree angle, so they are all right triangles, and since they line up over here at the right-hand end, they all must have the same three angles because this angle is the same, the right angle is the same. Mathematically, since they all have to add up to 180 degrees, they must all have exactly the same three angles. So now I've labeled some sides A, and they're all a little different because the green side A is a little bit smaller than the black side A, which is a little bit smaller than the blue side A. And there are sides B for the green triangle, the black triangle, and the blue triangle. And then there are sides C, which is the longest side of all, which has a special name. It's called the hypotenuse. So these triangles, since their angles are all the same, even though the sizes are different, there's a special name for these. These are called similar triangles. And similar triangles here are going to have this kind of interesting property that if I take the ratios of the sides, they have to be equal. So let me show you what I mean. If I take the ratio for the black triangle, side A divided by side C, that has to be exactly equal to blue triangle's side A divided by blue triangle's side C, which has to be exactly equal to green triangle's side A divided by green triangle's side C. So since these are all exactly the same, there's something a little bit special about that. It's a quantity that stays the same for a similar triangle no matter how big or small the triangle is. And we are going to define this as for all of these triangles, side A divided by side C is the cosine, which we abbreviate as COS, of angle beta. Angle beta is the one right here over on the right. Now we can go ahead and take a look at side B over side C. For the black triangle, that of course is equal to side B over side C for the blue triangle, and that is equal to side B over side C for the green triangle, and this is equal to the sine, which we spell S-I-N, of that same angle, angle beta. So there's one last comparison so that I can complete this sort of triumvirate of trigonomic functions. We can compare sides A and B. So for angle beta, I'm going to compare side B over side A. That's going to be equal to blue triangles, side B over side A, which is equal to green triangles, side B over side A. Oops, look, I made a mistake on my blue triangle. I've been making them all C's before. That should be A. And this ratio is equal to, I'm going to have to write it below, tangent, which we abbreviate TAN, of angle beta. So like I said, this comes from the special property of similar triangles. When I first learned about sine, cosine, and tangent, I had this really goofy math teacher, but he was great because he would be really silly and it was very memorable. I remember him acting out this story about an Italian cowboy who was cooking on a campfire and stubbed his toe and said he needed to soak a toe. He needed to soak the toe to make it feel better. Well, that soak a toe turns out to be the phrase that many students use to remember these ratios of sine, cosine, and tangent. Because sine, cosine, and tangent, they seem kind of mystical. There's this right triangle, and we talked about similar triangles. There's nothing mystical about it. It's ratios. And the fact is they work for any right triangle because of some of those rules of geometry like similar triangles. So SOHCAHTOA, the first part, so, we have an S, which stands for sine, and O over H. This means that to find the sine of an angle, the ratio that we're talking about is the opposite side from that angle divided by the hypotenuse of the triangle. So let me explain the others, and then we'll come back to this. So ka is cosine, and then A over H. That stands for the adjacent side divided by the hypotenuse. Then TOA, T stands for tangent. Then we have O over A. So here's what this means. If I'm thinking about angle alpha in this triangle, which is this top angle, and I wanted to calculate the sine of angle alpha, then I need to take the ratio of the lengths of two sides. The sides that I pick are the opposite side, that's the O, and the hypotenuse. The hypotenuse is always the longest side of the triangle. That's usually the easiest to find. That's side C in this case. The opposite angle, well, let's see, here's angle alpha. We go opposite, that's going to be side A. If I wanted to find the cosine of angle alpha, SOHCAHTOA. Ka is adjacent over hypotenuse. Well, I definitely know what the hypotenuse is. That's side C. Adjacent means next to. So here's the angle. It has two sides that are adjacent, side C and side B, but side C is the hypotenuse, so we need to take the other one. So the adjacent side, which is the A in Ka, is going to be side B. Finally, to find the tangent of angle alpha, I need to take the opposite side, which was side A, and divide by the length of the adjacent side. Now you should be able to figure out what this table should look like for angle beta. Do you have it? Do you have it for angle beta? If we want to take the sine of angle beta, we need to take the opposite side over the hypotenuse. It's the same triangle, so the hypotenuse is the longest side, still side C. But the opposite side, well, here's angle B. We go opposite, that's side B. We're talking about a different angle, so there's a different side that's opposite. Cosine of angle beta is the adjacent over the hypotenuse. Well, hypotenuse is C. Adjacent, next to, there are two sides next to it, but we're already using C as the hypotenuse. So this must be side A over side C. And finally, if we want the tangent of angle beta, that's going to be this opposite side, which is side B from angle beta, divided by the adjacent side, which is side A, if we're talking about angle beta. So as a final part of this lesson, let me just run through an example of how we actually use sine, cosine, and tangent. So I've sketched out an angle. It is a right triangle here. It has a 35-degree angle on this side. This angle alpha, I didn't write down. I don't know what it is. It has a side here. This is the hypotenuse, the longest side. That's 2.5 centimeters. I can figure out everything else about this triangle. I mean, I can figure out the sides. Side A, side B. I can also figure out this angle. Let's start with the angle. In some ways, that's the easiest. Remember that if we add all the angles together, so whatever this angle alpha is, plus 35 degrees, plus 90 degrees, it all has to equal 180 degrees. Well, if we add up 35 degrees and 90 degrees, that's 125. 180 degrees minus 125, alpha must be 55 degrees. And so I can go ahead and write that in here so that I don't forget that I know it. Great. So now let's go ahead and figure out sides A and B. Well, we have these ratios, sine, cosine, and tangent. I know all the angles, and so I actually have choices. I have options here. I could use the 35-degree angle, and I remember that the sine of 35 degrees, sorry, I didn't write that right, 35 degrees is equal to the length of the opposite side, which would be side B, divided by the length of the hypotenuse, which is 2.5 centimeters. Well, there's only one unknown in this, so I can solve it using algebra. I'm going to multiply both sides by 2.5 centimeters. So 2.5 centimeters times sine of 35 degrees has to be equal to side B. I can go ahead and put this in my calculator, and I find that side B is equal to 1.4 centimeters. Alright, so now we can go after side A. We've got two angles to choose from. I can use sine or I can use cosine. I've already used sine, so how would I use cosine? But cosine of what? So cosine, so, ka, toa. Ka, it's an adjacent side that I want to use with cosine, so I'm going to use this 35-degree angle again. So this time I've got the cosine of 35 degrees. This is going to be equal to the length of side A, the adjacent side, divided by that hypotenuse, 2.5 centimeters. I'm going to multiply again both sides by 2.5 centimeters. That's going to equal the length of side A. Put it in my calculator, and I find that side A is equal to 2.0 centimeters. Now, there's more than one way to do this. I could have brought tangents into it. I could have used the 55-degree angle instead of the 35. But we got everything we needed using these ratios of sine, cosine, and tangent. And that concludes our lesson on sines, cosines, and tangents.